we somehow extend the representation to the whole Poincare group. And in this case, instead, we want to start from the Lorentz subgroup of the Poincare group. So we will start with constructing unitary reducible representation of the Lorentz group, and we will exploit this isomorphism with the conformal group, and then we will extend this representation to the whole Poincare group. And in this way, we obtain a different way to construct unitary reducible representations of the Poincare group, and in this way, we make manifest all the properties with respect to the Lorentz group. This is the reason why on the QFT side, we have this reformulation in which everything is like in a CFT manifest language. This is actually, I want to point out this fact that in this presentation, celestial holography is just a reformulation of quantum field theory. So there's nothing that involves holography at all, actually. However, during the celestial sphere is two-dimensional. Yeah, we drop one eye here and one unit here and one unit here. And we pass from conformal group on the Euclidean, a d-dimensional Euclidean space. So this is going to be an Euclidean CFT, a d-dimensional Euclidean CFT. And the celestial sphere is just R to the D. It's represented as R to the D. The celestial sphere is going to be a new parameter space. So we are just replacing the momenta as a parameter space with the celestial sphere. Okay. So this is just another formulation, but this is, I mean, this is not trivial because this is the first time which we consider something, I mean, in non-relativistic quantum mechanics, we often use several bases, several descriptions. In quantum field theory, we are, let's say, stuck with this thing of considering particles as labeled by their momentum. And of course, several connections with holography will emerge, and in particular with ADS, or actually Euclidean ADS holography. But I don't have time to discuss this part here, but I just want to say that somehow, if you consider an Euclidean ADS space, you can always embed this space inside the light cone in Minkowski spacetime, this double sheet hyperboloid, and we can see that somehow Euclidean ADS holography lives on this hyperboloid, and for several reasons, it seems like that celestial holography extends all the results from this hyperboloid to the whole Minkowski spacetime. So celestial holography is a kind of analytical extension to the whole Minkowski spacetime of Euclidean ADS holography. This is quite interesting, and I'm working in this direction. But in this presentation, I just want to point out, let's say, representation theory underlining celestial holography, and the best way to do it, in my opinion, is starting with Weinberg's approach to quantum field theory. In the Weinberg's approach, everything is recovered by just considering something that is not local at all, which are unitary irreducible representation of the Poincare group. And of course, in quantum field theory, since we want a local theory, and a causal and local theory, and of course we want to create and annihilate particles, we are led to consider, to define objects that transform, that are actually local operators, and that transform covariantly under the action of the Poincare group over the Minkowski spacetime. So here we have this covariant field irrep of Poincare. And of course, what we do, we start with deriving the solutions of the Klein-Gordon equation, and of course, these are the classic solutions. And then we promote these guys to operators, and so we have creation and annihilation operator, and we can always split a generic solution as a sum of positive and negative energy solutions in this way. But here we have already promoted this guy to be an operator, and so acting on the vacuum of Minkowski, we have this equation here, and on the right-hand side, we have something pretty different. It is non-local, and this is a Wigner particle. So in this approach, somehow, quantum field theory emerges from intertwining together these two irreducible representation of the Poincare group. And the object that we need to, the intertwiner, which is this one, this is the intertwiner, or if you want, the intertwining operator, is that object that allows us to glue together these two representations. Now, we know how these guys here on the left-hand side transform. Actually, we demand that they transform in this way, as in equation 1, because we are saying that they are fields over Minkowski, and this is just the usual covariant transformation law. And on the left-hand side, we are saying that these guys are actually operators. On the other side, this is taken from the seminal work of Wigner. We know how these objects, this Wigner particle, transform, and we can also review later how to construct this irreducible representation, unitary and irreducible representation of the Poincare group. But essentially, they form the one particle Hilbert space. They are asymptotic states. And this is the transformation law, which is pretty different. And I don't want to enter in detail, but these matrices here, they furnish a unitary and irreducible representation of the so-called little group. We are focusing here in the case where m is greater than 0. And so this is kind of, so this sigma is with respect to the little group, which in our case is SO d plus 1. So this index, this is the spin index, refers to this little group, not to Lorentz. The spin index that refers to Lorentz is this one, is L. And as you can see, this intertwiner, indeed, it has two spin indices, sigma and L, and also two arguments, because, I mean, it has to glue together these two representations. And how, I mean, to define the transformation, to find out the transformation law of this U, we have to just glue together equation 1 and equation 2, which are known, and we find that this is how this U transforms. And in this U, it's like it belongs to the tensorial product of these two irrep of Poincare. But without entering in detail, the nice observation is that under translations, since Wigner particles get a phase under translations, we have this transformation law here, under translations. And actually, from this equation, we can just strip off the plane wave from the definition of U. And this guy here is the so-called polarization tensor. Even though it does not transform as a tensor at all. Okay, it has two spin indices. Now, here, okay, now we are arriving to the key point. This is the Weinberg approach, but the point is that if we change, for example, either one of these two equations, for example, in this case, we will keep equation 1 because we want that these guys are local operators that transform covariantly in Minkowski. But if we change the representation here on the right-hand side, which is the Wigner, this is a specific representation, the one that we actually know from the literature. If we change this representation, this U will change as well. So if we define new states, these new states are I like to call this elementary. No, the Casimir is always the Casimir of Poincaré. Now I'll show you how to construct these guys. These states belong to both a unitary and irreducible representation of the Poincaré group and of the Lorentz subgroup. Both. Instead, Wigner particles, they belong to unitary irreducible representation of the Poincaré group and of the little group. So somehow Lorentz is good. Here we want to keep Lorentz untouched. And the nice thing is that if we replace this P with this, we have also as well replaced this U with something else. And this something else, as you can see, we are just replacing plane waves with something else. And these new wave functions are called conformal primary wave functions. These are the conformal primary wave function. And this is precisely the new class of basis that is commonly used in the context of celestial holography in place of plane waves. Of course, they originally they have been constructed not in this way, by using just equation of motions and so on. And the nice thing is that these guys transform in this way. So how I'm saying that under the action of the Lorentz group, they transform with respect to the second argument, the one that is replacing P, as conformal primary operators. Because the parameter space is the celestial sphere, and Lorentz is acting on this d-dimensional manifold as the conformal group. This is the reason. So on the, let's say, on this side, that is the parameter side, they transform as conformal primary operators. And with respect to the space-time, the action of Lorentz on the space-time, they transform in the usual way. So in this case, for example, I'm considering a vector. But also these guys, as you see, they have two spin indices. The one with respect to the space-time, or if you want, with respect to Lorentz, and this one is with respect to the, let's say, another group that in this case is SOD. Because, I mean, this comes from the fact that we are constructing irreducible representation actually of the conformal. And now we see how to construct this. Okay, if you have questions, I don't know. In this case, P square is fixed. Yeah. We are going to trade the P with something else. We are not losing the Casimir, we are losing the P. Indeed, here, all the properties with respect to the other subgroup, which in this case is the... No, I have free particles, but not in the usual sense. I mean, I still have cluster decomposition, but cluster decomposition, I could say that it's just this formula here. And I'm going to rewrite this formula, not using this P, but using something that maybe don't have an intuitive physics representation, if you want, interpretation, sorry. Maybe. Actually, in the massless case they are eigenvectors of the boost operator. In the massless case. In back of your mind. Yeah. Indeed, the celestial holography as a framework is much more explored in the massless case. But I'm working in the massive case where everything is a mess. It's less intuitive. But this connection with ADS holography comes out in the massive case really in a very clear way, and you really are able to understand the nature of celestial holography. The massless case is just another case. It's easier for many points of view. for many reasons. But if you want to work out this connection with ADS, you have to consider the massive case, because the hyperboloid, this one, in the massive case, you have a physical interpretation for this hyperboloid, because this is the mass shell parameter space, only in the massive case, this one. And so what we are doing, actually, we are using holography, really, ADS holography, in the parameter space. Because in the parameter space, we have, this is our parameter space, so it's like holography is defined on this hyperboloid, and we are just trading points in the bulk of this hyperboloid with other points that live here on the boundary, which is the celestial sphere. And you can think the celestial sphere as something that if you just use light rays, as you said, you can construct a light ray in this way that intersects a point P here, then proceeds towards infinity, and at infinity, let's say it intersects also the section at infinity of this hyperboloid. So it's like a circle at infinity, the celestial sphere. But here we are representing celestial sphere as R to the D. Why? Because here we are using a stereographic projection. So the celestial, I'm projecting these points at a finite distance to points on a plane at infinity. This is the idea. And you are just using actually ADS holography in the parameter space. How much time I have? Okay. All right. Okay, let me write this. Okay, so Wigner with elementary. Okay, now I'm going to show you how to construct these two representations, and I also want to show you the differences. So for the starting point is always the same. So I want these states that diagonalize the Casimir operator. And this is the same story. Let me call this. Here there's a number. And something else. Okay, this is ISO 1, D plus 1. And then on this side, I also diagonalize the P mu. This is the point. But actually, first, we consider a reference momentum. Yeah. Don't look at this for the moment. This is unknown. Just for the moment, let's just stick with this part of the blackboard. So I have the mass. The mass is fixed for any state. Then I consider this particular reference momentum, which is just a reference momentum, and then I diagonalize the generator, the translation generators. Then I consider the little group. The little group is that group that leaves this vector invariant, which is just an SOD plus 1 subgroup. And so I have J, Ij, acting on this K. I have matrices that, of course, these furnish unitary and irreducible representation of the little group SOD plus 1. Yeah, the S is like in this spin label. If you want to put an S here, okay? Yeah, it's everything in this. We are in generic dimension, so yeah. Yeah, it's not, then I can find all the other states in the same rep, just boosting. So what I have to do is to define P. This is the usual construct. Yeah. Yes. So these are all the other states. And then you can use all of these relations plus the commutation relations to derive the action of the generators on these states. These are all the states in the same irrep. And we can do the same on the other side. But here, what we exploit is something that we already know in literature regarding how to construct irrep of Lorentz. Lorentz, in this case, is just the d-dimensional conformal group. So we are considering this basis of generators. We have the dilation generator. Then I have this d-dimensional translation generators, this p tilde A. Then we have the special conformal transformation generators. And then we have J, A, B. These are generators of S, O, D. And we can do the same story. In this case, we consider the reference in R to the D is we are considering the origin in this new manifold, which is our new parameter space. And then again, we diagonalize in this case the dilation operator. And then I consider the action of this Ka. This guy has to annihilate these states. This is the usual lowest weight, let's say, assumption that we do when we construct irrep of the conformal group. And then we apply the rising operator that is this guy here. And we construct all the others. So we start from this condition, and then we can construct all the tower of states in the same irrep. This is not actually essential. You can also, consider a generic action, but this is the usual way to construct this irrep. But don't focus on the details. I just want to show you that in this case, this A is an index with respect to this group here, SOD. Okay? And then we find all the other states by boosting, which means that we are left with these guys. And so all the other states for any W belonging to R to the D are found just exponentiating this P tilde A in this way. And also in this case, you can work out all the action of all the generators on these states using the commutation relations between them and these assumptions. So this is the way we construct these states. So these labels are delta is the label with respect to D, and importantly, any irrep of the conformal group can be constructed starting from this one. But there are specific ones that are unitary and irreducible. And in particular, in our case, we restrict to delta, which in general is a complex number, to this series that is called the principal continuous series. Only for delta belonging to this series, this is a unitary and irreducible representation. No, actually there are other series exist, but it turns out that in our case, this is the right one. Why? Well, I'll try to justify this in a moment. But this is the construction, more or less. And of course, this is very abstract. But now, the last part, and then I can conclude with my talk, I hope that I'm still in time, is how to derive these, concretely these states. We are just using this is a non-unitary T in the usual ADS let's say, vision. I mean, it says, yeah, okay. This is not unitary with respect to ADS, but not respect to Euclidean ADS, because here working in Euclidean ADS space directly. In ADS holography, you start from the group SO 2, D. this is the isometry group for ADS. Then what you do is to weak rotate to SO1, D plus 1, which is the isometry group of Euclidean ADS. So all the unitarity bounds, all the, the properties of this CFT as physical CFT are realized here in ADS, not in Euclidean ADS. And in that case, you find that actually you need the delta must be real and greater than a delta minimum. This is the usual unitary. Here you don't have this fact because here you start that. This is an important difference, and people is still confused by this. They don't see why. This is a different CFT in the sense that we are already, because there's Lorentz behind. There's the Lorentz group behind this story. This conformal group is fake. We are diagonalizing the Lorentz group, the Euclidean conformal group, if you want, not the Lorentzian one. Okay, just the last thing. I just want to use all of these relations here. I don't remember this number actually, but the point is that this, all of this is, okay, here, sorry, there's a missing point that is important. I also have to diagonalize the Casimir of Lorentz, first of all. So in this list, we have to add this very important, actually essential condition that here you want something that, okay, here, yeah, I thought that this was the Casimir of Lorentz. No, this is the Casimir of Poincaré, so this is a square. And here there's the unknown number that I don't remember, okay? So I'm diagonalizing both these Casimers. And then, of course, these are states in our one particle Hilbert space. So what we can do, in general, is that we can decompose these guys into plane waves, or Wigner states, if you want. And so, in general, we have a decomposition realized in this way. Here there's a sigma. This is the Casimir of Poincaré. This is P square. This is J square. J mu nu J mu. J square. Sorry for the notation. Yeah, this is J square. Okay, we have this. This guy here, in general, is this possesses two spin indices. I can write this guy in this way. This is another intertwining curve. But in yeah, it's not diagonal. Yeah. Here is not diagonal. Here it is. This is the main difference. Here, what is that? We are trading P mu, this, with all of these conditions. And I guess that if you count, they are the same number of operators. Yeah. Yeah, exactly. Yeah. D of this, small d of this, but these are all trivial. But you should count d of this plus 1 plus 1. So it's d plus 2, also in this case. No, but this is really confusing. I mean, you can use it if you want, but in that case, I'm just directly diagonalizing the literal. I'm supposing that I already know that that condition is useful to find out this sigma. I'm supposing that I already know those sigma. So this is that one should be an additional condition, but it's not independent from the others. So you can always rewrite that W square in terms of the conditions, the eigenvalues that you see here. Okay. I just want to conclude because I guess I'm running out of time. Here I'm decomposing, of course, we have a basis, our old basis. And so if you just plug this decomposition inside the condition on the Casimir, you obtain the action. You can just use the linearity of the Casimir. So I'm just plugging that expression here. Then I use the linearity to bring the Casimir inside the integral. And then the Casimir of Lorentz will act on this state here. And what we get is that we are obtaining, after projecting everything in momentum representation, a differential equation. This is the point. A differential equation, which is what we solved in our paper. I'd like to write down this differential equation, but I don't think it's important. I mean, it's this one. What we get is for any state is that I update this differential equation. Just want to write here there's a number, and it's not important, this number. Of course, it's known. I mean, with this. And it turns out that this guy, especially in the scalar case, which is the most simple situation, is precisely, it's known, and is the bulk to boundary propagator in Euclidean ADS. So the main ingredient to construct ADS holography. The bulk to boundary propagator is that guy that when we consider Euclidean ADS, this is Euclidean ADS from the above. This is the so this is the bulk is Euclidean ADS. The boundary is the celestial sphere, as I have drawn before. And so the bulk to boundary propagator is that propagator that allows us to connect one point in the bulk with one point on the boundary. And this is used to construct diagrams in Euclidean ADS holography. This is in the P. This is the Laplacian in the P. I have projected everything using on the left on the P's. So, yeah, W is W. Let me check. No, actually no. This is the different. This is just a number which depends on nu and on the spin, of course. Yeah, but this is known actually in literature. But we have, of course, in the scalar case, it's simple to solve this equation. But in general, it's not trivial because we have two spin labels, and it's like we are decomposing things not only in the space of the P's, but also in the space of the spins. Is that let me see. No, sorry. Well, the solution in the, for example, yeah, I mean, the point is that here, this W lives on the boundary. Okay. Yeah, it depends on that. Yeah. Yeah, I was saying that since this W lives on the boundary, Yeah, also because actually, strictly speaking, this is not enough. There's other two conditions that must be satisfied, which is that this guy is like delta renormalized. So it's like, I mean, you know that when you have a, yeah, but this is, the important thing is that you, to characterize an Hilbert space, you also need a resolution of the identity and an inner product. All of these things. So in this case, what does it mean? That in this you have a measure in nu, then you have an integral over the W, and then you have these states in this way. Here there's a scalar product. Now, when you project everything using the P, this becomes a condition on G. And just sandwiching everything between the P's, you get like something like this, which is another condition that you have to impose, actually. G star, let's say. So the product of these two must be a delta function. Okay? This is omega prime, and this is W prime, and this is stuff. Okay, this way. So you have this also, you have also to, this is a kind of boundary condition. And the inner product also between these P's gives you other delta in the P. I mean, you need to impose the resolution of the identity and also that. No, sorry, I'm wrong. No. This is delta in the P's. Let me write this carefully. Say P prime. So this is a delta in the P, and this condition here is that this one, which is another, this is the condition of the inner product, gives you other constraints. And this is enough to totally fix this G. And this is precisely the actually, this one also fixed the principal continuous series. So everything is, you can derive everything just considering 1, 2, and 3. You can fix everything. Well, when you, well, okay, the point is that you have this one is, let me write the solution in the scalar case, just to give you the solution in the scalar case. So you have this P is 1 over minus 2. Here I have this weird scalar product. We are embedding this guy. This is the point. This, you have somehow to embed this W in a space where also P lives to satisfy all of these conditions. So you are saying that this W lives on the boundary of ADS this way. So you have to embed in the same space of P, and you obtain this. There are a lot of work on that. The differential equation is in principle, actually this is the point. So we already knew the solution actually. But in the spin case, I mean, I don't want to enter details, but you have to use another approach that is called embedding formalism, and in particular the so-called free index embedding formalism. So there are a lot of work on this of Penedones, Richkov, and so we got all the results from there, and we have just glued everything together to get our final answer. I was checking for further details on this differential equation. I can provide you with further details later. Okay, so just okay. Yeah, the physical meaning. I mean, we are talking about ADS holography. Okay, so the idea is that when you have a quantum field theory on a compactified manifold, I mean, you need two types of propagators. The bulk-to-bulk propagator that connects 2 points in the bulk, which is the analogous of the Feynman propagator. And then you have the bulk-to-boundary propagator that is obtained by taking 1 point and sending it to the boundary. Now, the point is that this boundary is there, but is not really there, because you have to shrink points at infinity to a finite distance. So there's a kind of behavior, divergent behavior of all physical objects when you try to reach infinity. So, for example, this bulk-to-boundary propagator becomes a delta function times a power of a coordinate, which parameterizes like the time when you try to reach the boundary. So there are several conditions, but I guess that you can. I mean, this is enough actually. So all the conditions that are required are here. Equation 1, 2, and 3. This inner product here is always greater than 0, minus 2 q dot p for any p on the hyperboloid inside the electron. And this guy can be 0 only when p coincides with q. Q is a null vector. So only in that case, and in that case you get the delta function. Mm-hmm. The dilation. Delta is inside this number. Yeah. No, indeed, because that nabla square, yeah, it is like in the bending formalism that is a nabla square. Yeah, you have, first of all, you have to embed everything in the same manifold, compactified manifold. So there are some projection inside this nabla. Actually, I was looking for the expression of the nabla, but I'm not able to find it. But it's somewhere. Yeah, this is the problem. But it's somewhere here. I'll show you later. Yeah, but trust me, this is the solution, because this is known. I mean, you can also ask Penedones. Yeah. Okay, so this is it. I mean, I just wanted to show you how to introduce celestial holography in just a very messy way using just representation. Okay. Okay, first of all, we in this way, in my opinion, we have clarified many aspects of celestial holography, because the point is that once you have defined this G, you can pass from these new elementary states to the P's and and vice versa. And you can, of course, derive, in this way, you can derive all the formulas that are already present in the literature, first of all. The definition of conformal primary wave functions can be derived in this way. And then, of course, you can also use this story to bootstrap something, in my opinion. So the next step, in my opinion, would be, okay, we already know now how to deal with these new states. We can try to consider, for example, 2 processes, amplitudes, and bootstrap everything only using the properties of these guys, considering the 2-particle Hilbert space, and decomposing into this event, not the Poincare one, to really to see the content of celestial holography at a bootstrap level, for example. No, this is not holography at all. For the moment, we cannot say, in my opinion, we cannot say this is holography. In my opinion, I can say there's a strong connection with holography, of course, but it's not enough. So this is a scenario that must be completed somehow. And I'm working also in that direction. So the idea is now, Minkowski space that is not compactified. I mean, here ADS is compactified. Here we have just working Minkowski, just uncompactified. You compactify Minkowski, obtain the so-called Penrose diagram. And then, this is, in my opinion, the most natural formulation that we can use in the bulk to study processes, for example, in asymptotically flat spacetimes. Because it's quite natural in this formulation, pushing everything towards the boundary and considering the states as living on the boundary of our compactified spacetime. This is actually the direction of my future project. Okay, thanks.